So let's have a quick review of what we have learned in the last course. So basically, so we were talking about, the sample statistics, right? Say X bar or the sample proportion P hat and the sample variance S square, right? So we use those sample statistics to estimate the real population corresponding parameters. Say we use X bar to estimate the population mean mu. We can use P hat to estimate the population proportion P. And we can use S square to estimate the real population variance, which is sigma square. Okay? And we have mentioned that those parameters are constants in this class, right? Those parameters are constants, but like for most of the cases, they are unknown. Okay, they are unknown. However, those statistics, say X bar, P hat, and S square, we have proved that those stuffs are random. Okay, they're random variables actually. This means those sample statistics can have their own distributions, right? So for example, my population distribution, my population variable X follows a population distribution, say a normal distribution, with parameters mu and sigma square. Okay, and then we said the sample mean X bar, which is equal to a bunch of random variables of X, right? Say those Xi's or IID follows the normal distribution. So this X bar follows the normal distribution with mu and sigma square divided by n. Okay, and then we also said if the original distribution, that is the population distribution, is not known, say this one, we do not know the distribution, or we can say it's not normal, okay? But we know the mean and the variance, okay? Then we can say X bar, the sample mean, still follows a normal distribution with mu and sigma square divided by n. We add a dot here, which means approximately follows the normal distribution, okay? If the sample size n is large. So how large? We say in this class, we say if n is larger than 30, you can apply the above theorem. Okay, so the above theorem is called the central limit theorem. We call this CLT in short. Okay, it's very important, and everybody should know this. Okay, and also we discussed the p hat, right? The sample proportion. We use this one to estimate the population proportion, and because we know that the sample proportion can be written in this way, right? So each xi is equal to 0 or 1, 0 or 1. And if those xi's are IID, say Bernoulli, okay, then x1 plus x2 plus xn divided by n can be written as x bar, right? So the sample proportion essentially is just a special case of sample mean x bar. So we can apply all the properties of x bar that we have derived before to the sample proportion. Okay, so that's the basic steps that we have talked about in the previous section. After this, we're going to talk about this sample variance S square. Okay, so we're going to use this S square to estimate the population variance sigma square. Like we did before, we're going to do AM experiments or AM samplings. So in the first experiment, okay, just imagine you are rolling a fair die, or let's say let's say it's fair, okay? So we're rolling this die for n times. So n, say, is equal to 10. Okay, I'm rolling this die for 10 times, so I'm going to have 10 such random variables, right? So those random variables, I'm going to call this x1s, right? So x1j. Okay, why? Or I can say x1i. Okay, x1i. So the first one means the first experiment, the first sampling. Okay, and this I can be equal to 1, 2 until n. So n is equal to 10, right? So you're gonna have 10 such values, and then you can calculate the corresponding x bar, right? With the x bar, say in this case it's just x1 bar, right? So you have x11, x12 until x110, right? Okay, you have 10 such values, so you can calculate the average value for the first experiment or for the first sampling, right? And using those x1i's and this x1 bar, and we know this n, right? So you can have the sample variance, which is S1 square of the first sampling, okay? And then you write down this number and you do the second experiment. So basically you're repeating, like you're repeating the first experiment, okay? So for this time, I'm going to use 2 to denote my random variables, okay? So x2i's. Again, you're gonna roll the same die for 10 times. So you're gonna have x21, x22 till x210, right? And then you can have your x2 bar, and you can also have your s2 square. So if you do this for m times, right? So within each experiment, you will have 10 such values, right? So xm1, xm2 until xm10. Okay, and then you can have your x10 bar. You can also have your s10 square. Oh, sorry, not x10, xm. Right, just to make sure you can tell the difference between m and n. Right, so n is the number of rolling, right, within each experiment, and m is the number of experiments. So, you know, the sample size that we have discussed for the x bar, right, is this n. It's not m. Okay, just make sure that you can tell the difference between these two. Okay, then you can have your xm bar and you can have your sm square, right? So basically, if you're repeating sampling for m times, you can have m s squares, right? So those s squares are expected to be random. Okay, so we can say s square, that is the sample variance, is also a random variable. Okay, it's also a random variable, like x bar, like p hat. Okay, so how can we use this random variable s square to estimate the unknown constant sigma square? Okay, that's our goal, right? Before that, I'm going to introduce you another distribution called chi-square distribution. Okay, so this distribution is a continuous distribution, okay? So a continuous random variable x has chi-squared distribution with parameters v if its density function is equal to this. So this is the gamma function, right? So it's a bunch of steps. So I'm not going to introduce the details of this PDF. However, instead of introducing this one, I'm going to introduce you another stuff. So another way to define this chi-square distribution. Okay, so we all know what is a z-random variable. A z-random variable actually is a standard normal random variable, right? Its expectation is equal to 0 and its variance is equal to 1. Okay, so if I square this standard normal random variable, so which is z squared, right? I let this one is equal to a new random variable. We call this chi-square distribution. with a degrees of freedom is equal to 1. Okay, so I'm going to like tell you or explain the exact definition of degrees of freedom later. Okay, so if I have, a bunch of such z's, say this is z1, okay, so z1 square follows is equal to chi-square distribution, okay, and say I have k such standard normal random variables. Okay, so I have z1 squared, z2 squared until zk squared. Okay, then I'm going to say, okay, so z1 squared plus z2 squared until zk squared follows a chi-square distribution with degrees of freedom is equal to k. Of course, those, zi's are IID. Okay, they have the same distribution. They are mutually independent. Okay, in this case, we will define this stuff as my chi-square distribution with degrees of freedom k. Okay, so you can take a look at this PDF. Okay, so first of all, it's continuous, and it's derived by the summation of a bunch of the square of standard normal random variables. So if you only have one squared, random variable, so you can see when k is equal to 1, so you can find the yellow curve, right? It looks like this. But when k goes up, for example, when it's equal to 4, say, you can check its PDF is the corresponding blue curve. It looks like this. Okay, definitely. Again, it's not symmetric. It's far away from the normal distribution, right? But that's a brief overview of this chi-square distribution. Okay, let's go back to its definition. Okay, on the slides. So it says chi-square distribution is also a special case of gamma distribution. So if you recall, for a gamma distribution, it has two parameters, alpha and beta, right? So when alpha is equal to v divided by 2 and beta is equal to 2. So you can find the corresponding PDF of gamma distribution can be written in this way. Okay, so actually this is the PDF of gamma distribution when alpha is equal to v divided by 2 and beta is equal to 2. Okay, so that's like the two ways to define a chi-square distribution. So this v you can treat as the same thing as k here, okay, as key here. So because we know that for a gamma distribution, its expectation is equal to alpha beta, and its variance is equal to alpha beta squared, right? So if you plug in the values of alpha and beta, you will find the corresponding expectation for this chi-square distribution is equal to v, and the variance is equal to 2v. Okay, so that's all the stuff that you need to know about chi-square distribution. Then, using this distribution, we can learn some properties about the sample variance. Okay, so we have this theorem. If S squared is the variance of a random sample of size n taken from a normal population with variance sigma squared. So in this case, this population variance sigma squared, say if it's known, okay, and we also know the S squared, which is the sample variance. Like ideally, we're going to use this S squared to estimate this sigma squared if it's unknown. Okay. Then we say we construct a new statistic called chi-square. So this chi-square is equal to n minus 1 multiplied by S squared divided by the true population variance sigma squared. So this statistic follows a chi-square distribution with v is equal to n minus 1. Okay, its degrees of freedom is equal to n minus 1, where S squared is equal to this thing. Okay? So the most important thing for this stuff is that your population distribution should be normal. Okay, so what does it mean? Because we have a S here, right? S squared. And S squared is equal to this stuff, right? So it's constructed by xi, x bar, and sample size n. So xi are drawn from the population, original population, right? Original distribution. So this stuff has to be normal. This stuff has to be normal. And based on this, you can have this theorem hold, right? If you do not know the distribution of xi, you will not have this conclusion. Okay, so in a word, xi follows a normal distribution, right? And then is sample variance, which is equal to this, has the following property. Okay, so you using S squared and the true variance sigma squared to construct a new statistic called chi-square. So this chi-square follows a chi-square distribution with degrees of freedom is equal to n minus 1. So that's the brief thing for this theorem. Okay, so let's take a look at example 8.7 using this theorem. Okay, so suppose that S squared is the variance of a random sample of n taken from a normal population with variance 2. So use the chi-square table, find the cutoff value C. Okay, so you may want to ask, what is the chi-square table? So this is a chi-squared table. Okay, this is a chi-square table. So as you can see from the graph, right, so it's a continuous curve, right? Basically, it's the PDF of a chi-square distribution. And the shaded area is the area of interest. So for example, if you want to make this area to be 0.05, right, then you can find the corresponding cutoff value. In this graph, it's just the chi-square. Okay, so I will use this example to show you how to read this table. Right? So first of all, you have to, like we said before, you have to make sure that your original distribution is normal, right? Okay, so let's check this out. All right, so suppose that S squared is the variance of a random sample from a normal population, right? From a normal population with variance is equal to 2. Okay, so we say x follows a normal distribution with variance is equal to 2. Okay, and then we know that S squared is equal to xi minus x bar squared divided by n minus 1. Okay, we would like to find the cutoff value C, right? Find the C such that the probability that S squared is larger than C is equal to 0.05 when n is equal to 25. Okay, so if you go back to this theorem, you're going to find here we have n, we have sigma squared, and this S squared is the probability of this S squared is what we want, right? Okay, so this whole stuff follows the chi-square distribution. So I'm going to construct this chi-square statistic using S squared. Okay, so this stuff is equal to, I'm going to multiply it by n minus 1, right, and divide it by sigma squared. Because n minus 1 is positive, sigma squared is positive, so you can multiply by this stuff without changing the direction of the unequal sign, right? So this is still larger than n minus 1 multiplied by c divided by sigma squared, right? So this stuff, remember, we call this one as chi-square, right? and it follows a chi-square distribution with degrees of freedom n minus 1. Okay, so I'm going to say this is equal to chi-square larger than c prime. So I call this whole stuff as c prime because c is a constant that we would like to find, right? N minus 1 is a constant. Sigma squared is a constant. So we can let those constants as a new constant called c prime. Okay, so I'm going to find this cutoff value c prime to make the probability to be equal to 0.05 using this table. Okay, using this table. Okay, so n is equal to 25, which means n minus 1 is equal to 24. So I'm going to, first of all, find 24 from the first column, which is the degrees of freedom. Okay, so you can find 24 here, right, in the middle of the screen. 24 here. Okay, so you're going to focus on this row, and then, because we would like to make the shaded area to be 0.05, so which means, you're going to find the 1, 2, 3, 4, 5, 6, 7, 8. The 8th column, which is chi-square 0.050. You're going to find the 8th column. Okay, and you find the intersection between the degrees of freedom 24 and the area is equal to 0.05. So which is 36.415. Okay, so you remember this number. Okay, so I'm going to say, okay, so my c prime is equal to 36.415. Okay, but this is not over because our final goal is to find the c instead of c prime, right? Once you know the c prime, you will find the value of c, right? Because n is equal to 25 and minus 1 is 24. 24 by c multiplied by 2 is equal to 36.415. So you can have your value of c, which is equal to 3.03. Which is 0.03. Okay, so that's the basic way to solve such questions. So similarly, for this one, I'm going to do the same thing, right? I'm going to find a cutoff value c such that the corresponding probability is equal to 0.01 with sample size n is equal to 30. So I'm going to construct a chi-square distribution larger than n minus 1 multiplied by c divided by sigma square is equal to 0.01, right? So which is this stuff is larger than c prime, which is equal to 0.01, right? In this case, the degrees of freedom is equal to n minus 1 is equal to 29, right? So you're going to use this table to find 29, the 29 from the first column, right? And you're going to find on 0.01, which is the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th column, right? So you're going to find the intersection between 29 and 0.01, which is 49.588. So using this number, you can find the corresponding cutoff value c. Okay, I'm not gonna show you the details about this one, but I believe you can do this by yourself. Okay, so that's how do we find the cutoff value c such that the probability that R squared is larger than c is equal to a wanted probability. Okay. All right. So the very last part of this chapter, which is called the t distribution. All right. The t distribution also has a very complicated PDF. Okay. First of all, it's continuous. Okay. And second is PDF looks like this. Okay. And it's the corresponding range is from negative infinity to positive infinity. And actually, we can define our t in this way. Okay, so its numerator is a ratio, right? Its numerator is a standard normal z, and its denominator, this capital V, is a chi-square distribution. Okay, with degrees of freedom v, and this small v is this degrees of freedom from the chi-square distribution. So basically, because we are using this chi-square and z to construct a t distribution, so which means this t distribution will have the same degrees of freedom as the chi-square distribution that we used to construct this t. Okay, so we say t follows the small tv. So this v is the degrees of freedom of this t distribution. Okay, and moreover, we usually use notation t alpha v to represent the cutoff value c, such that the probability that t is larger than c is equal to alpha. So it's pretty similar to what we have done for this example. Okay, so again, we're going to find this c, right? And this is your alpha, right? So I'm going to replace s squared by t here. Okay, so this c is this cutoff value. We use this notation, right? But not for this example, actually. Okay, we use this one for this example, right? So this c is t alpha v. Okay, and this is the corresponding PDF of a t distribution. So again, probably you can find this is pretty similar to the standard normal distribution, right? It's a bell-shaped curve, and it's symmetric with respect to 0 as well. Okay, so but as you can see from the graph, when the degrees of freedom is equal to 1, you will find this yellow curve. When the degrees of freedom is equal to 2, you're going to find the purple curve, and the degrees of freedom is equal to 5, you're going to find the blue curve, right? And when the degrees of freedom goes to infinity, you will go to the black curve. And this black curve is the curve of standard normal curve. So which means, so the degrees of freedom, which means the distribution of t is exactly the same as a standard normal random variable if the degrees of freedom goes to infinity. Okay, so we have the following properties of t distributions. So I'm going to use t to denote the t distribution, and its degrees of freedom is v. So each TV curve is bell-shaped and centered at 0. So this is exactly the same as a standard normal distribution. Okay, but what's the difference between the standard normal distribution and t distribution? Okay, we see the first one, the second property. So the t curve is more spread out than the z curve. Okay, as you can see from this curve, right? So the general width, right, which is the the width of the yellow curve, or the general width, or the mean width of the the purple curve, or the the blue curve, right? You can see overall they're wider than the black curve, right? Especially we go here, right? It's more spread out. Okay, the third property, as v increases, the spread of the corresponding TV curves decrease, right? As we can see from the graph. Okay, so the last property, when it goes to infinity, right? When the degrees of freedom goes to infinity, the sequence of TV curves approaches the standard normal curve. So the z curve is often called the t curve when degrees of freedom is equal to infinity. Okay. So that's the introduction of the t distribution. So probably you would like to ask me, why did we learn this, right? So we didn't introduce any specific details of this distribution at all, right? So what is this curve? What is this PDF, right? It looks like very complicated. Why do we use this? Why do we use this? Okay, and actually, it is widely used in this notation, okay, in this definition. Say, if you recall, the way that we define a z, right? So we have, if say we have x follows a normal distribution, right? So how can we like convert this general normal random variable x into a standard normal z? We use x minus the expectation divided by the standard deviation, which follows a normal distribution, a standard normal distribution, right? So that is to say x minus mu divided by sigma, right? Okay, and also we have discussed that x bar is sample mean, follows a normal distribution with mu and sigma square divided by n, right? As n is large enough. Okay. We can do the same thing for x bar, right? So if you use x bar minus its expectation divided by the standard deviation, which is x bar minus its expectation is mu, and its standard deviation is square root of this variance, right? So which is sigma divided by square root of n. So this follows the z distribution, okay? Now, I'm going to just erase them and write it down here. Okay, so z is equal to x bar minus mu divided by this stuff, right? Okay. So if you compare this t and this z, okay, just forget the above definition. Just forget about it, okay? Just forget about it at this stage, okay? And if we say t is equal to this stuff, of course they're equivalent to each other, okay? But right now you just need to focus on this. Okay, so if t, follows this stuff, is equal to this stuff, you compare this formula to this formula. You're going to find the only difference between these two parts is as we use as to write a t, and we use this sigma to write a z. Okay, then you started thinking, okay, so why do we use sigma to construct a z, and here we just use as to construct a t? Okay, actually that's the key difference between these two random variables. Not the key difference, but the key difference in applying these two random variables. Okay? So what do I mean is, okay, so like I said before, using this one. Okay, so like I said before, sigma is the population standard deviation, right? And sigma square is the population variance. In general, is unknown to us. Okay? And so, it's not common for us to know the value of sigma square. So if you just use this one to construct your to construct a standard normal random variable, right? So this part, in general, you will never know. So people started thinking, okay, so I will use s, right, to replace this unknown sigma, because we can know s, right? So s is drawn from the sample, so you can know s. So if I use s to replace this sigma, what will happen, right? So we're going to define this new distribution as t. Okay, so this stuff follows a t distribution with degrees of freedom n minus 1. Okay, we're going to use this formula all the time for the following chapters. Okay, we're going to use this formula all the time instead of the original definition. Okay, we're going to use this one more. Okay, we're going to use this one more. All right, so let's go back to the curve. Okay, let's go back to the curve and its application. So example 8.9. So if t follows a t distribution with degrees of freedom is equal to 10, find the cutoff value c such that the probability that t is larger than c is equal to 0.05. So again, like what we did for the chi-square distribution, we're going to use the same strategy. We're going to have a t-table. Okay, again, this t-table gives us the degrees of freedom, right, and the corresponding value of alpha. So again, so this is the curve, the PDF of a t distribution, which is symmetric with respect to 0, right? And this actually is the shaded area, right? This part is the value of alpha. So the corresponding, the corresponding cutoff value, we use t alpha v to denote this one, is the c that we want. Okay? All right, so in this case, this is my alpha, this is my v, and this is my cutoff value, right? So I'm going to find, okay, so 0.05 is here. V is equal to 10, right? And you find the intersection, which is, which is this one, okay? 1.812. Okay, so I'm going to say, C is equal to 1.812. And similarly, you can do this one by itself, right? So C is equal to 2.74764. Okay, so you prove this. Okay, you verify this. Okay, so that's how do we use a t-table. It's pretty easy, right? Okay, the next example, 8.10. So company claims to fill out cereal boxes with an average weight of cereal of 24 ounces. Assume that the weight of cereal per box is normally distributed. To check the claim, 16 boxes are sampled. The sample mean and the standard deviation are found to be 23 and 2 respectively. Claim is valid if this t is between this cutoff value and this cutoff value. Is it a valid claim? Okay, so first of all, let's check like what kind of conditions or what kind of information do we have, right? So we have, okay, so average weight is 24. And we also assume that the weight of cereal per box is normally distributed. Okay, and we draw a sample, and the sample size is 16. We also know the sample mean and standard deviation to be 23 and 2 respectively. So here, notice that the sample mean and standard deviation means the sample mean and the sample standard deviation. Okay, so this standard deviation does not refer to the population standard deviation. It refers to S. Okay, so we have, if you use X to denote the weight of cereal per box, okay, so X follows a normal distribution, right, with mu and sigma square, right? And then we draw a sample, which is equal to 16. Okay, and we know the sample mean is equal to 23, and standard deviation is equal to 2. Okay, and our claim is to check whether this t is within this interval. Okay, because this is the alpha in the table, right? This is the v in the table, alpha in the table, v in the table. Okay, and you can see actually this value and this value, these two values are symmetric, right? Okay, so using those information, I can construct my t, right? Remember, we use this formula very often. So x bar is 23, right? Minus mu is 24, right? We know the true average weight is 24. Okay, divided by 2, divided by square root of 16. So this value is equal to -2. Okay, and then I'm going to check whether -2 falls into this interval or not. Okay, so what is the value of t, 0.05 and 15? Once you know this, you're going to know this one by adding a negative sign, right? Okay, so alpha is equal to 0.05 and v is equal to 15. I'm going to find this table. So v is just one more thing. Okay, so make sure you know that this one follows a t distribution with degrees of freedom is equal to n minus 1. Okay, this is n minus 1. But for this one, you just need to know that this v is 15. It's not n minus 1. Okay, so this is 15. So you're going to find 15 here, and you're going to find 0.05 here. So the intersection is 1.753. Okay, so basically this question is to ask whether negative 2 belongs to negative 1.753 to 1.753. Does it belong to this range? No, right? It does not belong to this range. So the claim is not valid, right? Okay. So that's the example 8.10. And that's all for chapter 8. Okay, that's all for chapter 8. So let's just have a brief summary of this chapter. Okay. So first of all, the big picture, we have a population distribution, right? A population distribution. Say we do not know the population distribution, and we know its expectation variance, or we know other parameters. Okay, so those parameters are the things that we're interested in, and those parameters are constants. So which means they're fixed, but for most of the time they're unknown, right? So our strategy is to find some sample statistics to estimate. So, for example, could be mean, could be variance, could be sample population proportion, right? We can find the corresponding sample statistics to estimate the corresponding parameter of interest. Unlike those parameters, our sample statistics are constants. Are not constants, right? They are random variables. They are random variables. Okay, so those parameters are not random variables. They're constants, but you know the sample statistics that we're going to use to estimate those parameters are random variables. Since they're random variables, they will have their own distributions, right? Okay, so because we know the population, the population random variable, we do not know the population random variable, but we can still know, the distribution of the sample mean, right? So it's equal to this, right? According to CLT, if the sample size n is large by CLT. Okay, but notice that even if this n is not large, you still have the conclusion that the mean and variance of x bar is equal to this, right? The only difference is that if n is not large and the original distribution x does not follow a normal distribution, you will not know the exact distribution name, but you can still know the corresponding mean and variance of x bar. Okay, so that's all for the distribution of x bar. And similarly, I'm going to use p hat to denote the sample proportion, right? I'm going to use p hat to estimate the p. So each xi is a Bernoulli random variable, so 0 or 1, 0 or 1, right? So it's a special case of x bar. Okay, and the last thing is s squared. I'm going to use s squared to estimate you know, the population variance. Okay, and we introduced you a new distribution called chi-square distribution. Okay, so we have this property. So this one follows the chi-square distribution with degrees of freedom n minus 1. Okay, so you can use this property to find, you know, the cutoff value given the wanted probability. Or you can find the wanted probability given a cutoff value, right, using the table. Okay, and the last thing is the t distribution, right? So for a t distribution, remember for a z distribution, we can use x bar to construct a z distribution, right? So t distribution is pretty similar to this one. The only difference is that we use s to replace this sigma, because this population parameter sigma in general is unknown to us, but we can have this s, right? So I'm going to use this s to replace this one. So this one follows a t distribution with degrees of freedom n minus 1. Okay? And that's only a brief introduction of this distribution. And in chapter 9 and 10, we're going to use this distribution for many, many times. Okay, so that's all for chapter 8. So from chapter 9, we're going to start a completely new chapter, a completely new part. Okay, like I said before, like in the beginning of the semester, I said this class can be divided into 2 parts. So the first part is called the probability theory, right? And the second part is called statistical inference. So from chapter 9, we're going to start our statistical inference part. Okay, so that's all for chapter 8.